everyone, I am Leodilia Solarte.
And I am Hasmin Sabanal.
I am Jhe-an and today we will discuss about transfinite induction.
Good morning, class. Faith, please lead our opening prayer. Again, good morning, class. How are you today? Please arrange your chair and pick up some pieces of paper underneath. Okay, you may now take your seat. I will check your attendance first. Classroom secretary, who are absent today? Very good. No one is absent for today's discussion. Before we begin, reminders for everyone, our rules in the class. First, give respect to each other. Second, listen attentively, especially when the teacher is discussing. The third one, instead of bothering your seatmates, raise your right hand if you want to participate, to ask questions, or to excuse. Do you understand, class? Before we proceed, let me ask you first, what was our topic last meeting? Yes, Maria. That's right. And who can tell me what this ordinal number is all about? Yes, Ryan. That's right. Yes, Shekinah. That's also right. How about Marilyn? Very good. That's concise yet understandable. How about giving an example about ordinal numbers? Yes? Rochelle? Very good. After listening all your responses, makes me feel that you are now well educated on our last topic, and you are now ready to enter a new door of learning. Okay, so are you now ready, class?
Yes, ma'am. Yes, ma'am.
Because I will now start the engine so that we can now move on to our new topic.
Since you already grasped the content of our previous topic, I will now group you into 3. So let's start counting at the back, okay? 1, 2, 3. Okay, since you're done counting, you will now go to your group. Form a small circle. So group 1 will be here, group 2 and group 3 at the back. So provide a small circle, ha? Okay. Then after that, you are about to choose your leader and secretary. So in this activity, groups who can provide the correct answers of the given activity will have points, and you will just given 5 minutes. So here's your activity.
Okay, so the direction for this activity is you'll get one whole sheet of paper, so complete the order of the following set given each item.
Based on our activity, what do you think will be our new topic for today? Yes. Thank you. So today we will be now tackling another topic, which is transfinite induction. So as what Miss Joella said earlier, it is related to well-ordered sets. So before we're going to discuss our new topic, may I call on Miss Pacaro to read our objectives. Miss Pacaro, please read.
At the end of the lesson, the students should be able to, first, discuss the concept of transfinite induction and its application in mathematical proofs. Second, use transfinite induction to prove statements about well-ordered sets. And lastly, apply transfinite induction to solve problems involving infinite sets.
Okay, thank you, Miss Pacaro. So that will be our objectives for today's new topic. But before that, let's have another activity. So each member of the group will receive an index card. So you are about to write down the examples of well-ordered sets, specifically involving infinite sets. Afterwards, the leader will now going to collect the index card from his members. So choose only 5 examples and choose your representative to discuss here in front your chosen examples. Then you will just given 10 minutes in this activity, and here's your rubric for this activity. Okay, time's up. So let's now present your output. So the first presenter will be group 1, followed by group 2, and group 3 will be the last presenter. So group 1. Okay, job well done, people. So give yourself a round of applause. So now let's proceed to our new topic for today.
Transfinite induction is a powerful mathematical technique used to prove statements about infinite sets, particularly those that are well ordered. It extends the concept of mathematical induction, which is commonly used to prove statements about finite sets or natural numbers. In transfinite induction, instead of proving a statement for each natural number in a sequence, we prove it for every element in a well-ordered set, including those beyond any finite number. The key idea is to establish a base case and then show it if the statement holds for all preceding elements, it also holds for the next element.
The foundation of transfinite induction lies in a well-ordered. A well-ordered set is a set in which every non-empty subset has a least element. One of the most popular or familiar example of well-ordered set is natural numbers. So to prove a particular statement, we use transfinite induction. So by using transfinite induction, we follow its basic idea or step. The first one is the base case. Here, we establish that the statement holds for the smallest element in the well-ordered set. And the last one, or the other one, is the inductive step. Here, we assume that the statement holds for all preceding elements. We show that it also holds for the next element in the well-ordered set. So, for example, let's consider the concept of ordinal, or the property of successor ordinal. In set theory, ordinal is a well-ordered set in which every element is strictly smaller than the set itself. So when we talk about successor ordinal, or it can be obtained by adding one more element to a smaller ordinal. So by using transfinite induction, let's prove this example aligned to successor ordinal. So this statement prove that every ordinal is either a successor ordinal or the smallest ordinal. So by using the basic idea of transfinite induction, let's first have the base case. Here, we show that the statement holds for the smallest ordinal, which is 0. 0 is the smallest ordinal. 0 is not a successor ordinal since there is no smaller order than 0. So here, our first element is 0. So in inductive step, here, we assume that the statements hold the next ordinal. Consider the next order 8 plus 1. If 8 is 0, then 8 plus 1 is a successor ordinal. Here in inductive step, the statements of all preceding elements also holds for the next element in the well-ordered set. So at what I said earlier, when we talk about successor ordinal, it can be obtained by adding one more element to a smaller ordinal. So we have our smallest ordinal. If you are going to add one more element, like for example 1, here 1. 1 is a successor ordinal since there is smaller order than 1, which is 0. So if you are going to add another element, which is 2, 2 is also a successor ordinal since there is also number that is smaller than 2, or 2 has a number is greater than 1 and 0, and so on. So by using transfinite induction, we prove that every ordinal is either a successor ordinal or the smallest ordinal. 0 is our smallest ordinal, and 1, 2, and so on are the successor ordinal.
Another example.
Prove that every infinite subset of a well-ordered set has a countable subset. So let's prove this statement by using the base case and inductive step. Here in base case, we consider the smallest infinite subset of the well-ordered set. Since it is infinite, we can choose any element from the subset as the first element of the countable subset. In inductive step here, we assume that for any infinite subset of a well-ordered set with order type A, there exists a countable subset.
Now, we also consider an infinite subset with order type A plus 1. Since the subset has order type A plus 1, it has the largest element. Let's call it X. Then, we can form a countable subset from the first element of the subset by using the assumption of inductive step and adding the element X to it, which is our largest element or largest number. Now, in inductive step, it said that all preceding elements also hold the next element in the well-ordered set. Now, let's just say that our elements. So we're in our. Let's say that B is a subset of A and C is a subset of B, wherein C is a countable subset. So our set A are the set of all whole numbers, and B are the set of all natural numbers, wherein B is a subset of A. Now, it was said here that we can choose any element from the subset as the first element of the countable subset. Now, let's just form a countable subset where it is divisible by 3. So, it said that we can choose any you can choose any element from the subset as the first element of our countable subset. So, since we are targeting the number or countable subset that are divisible by 3, let's have our first element as 3. Now, it said that we can form a countable subset from the first 8 element of the subset by using the assumption of the inductive step. So, what is a number that can be divided by or divisible by 3, which is greater than 3? So, let's have 6. So 6. It said also here that we can form a countable subset we can form a countable subset from the first 8 elements of the subset using the assumption of the inductive step and adding the element X to it, wherein our X is a largest element. So let's say our largest element is 27. X is 27. Now, we are now by using the assumption of inductive step. So we are going to add one more element in order for us to reach the largest element, which is 27. So 3, 9, 12, 15, 18, 21, 24, 27. So now we have our countable subset. The countable subset is a finite number of elements or infinite number of elements that has one-to-one correspondence to a counting number or order, or it has a bijection between an order or counting numbers. So 3, there is a bijection. Since 3 is our first element, 6 is our second, 9 is our third, and so on. There is a bijection. 3 must be the first element since it put here as the first element of our countable subset. Now, we be able to prove that every infinite subset of the well-ordered set has a countable subset. Now, let's have another example using transfinite induction. So, prove that every countable subset of a well-ordered set has at least upper bound. So, using can anyone provide an example of countable subset? Yes, Mr. Justin? Okay, thank you. So, we are going to prove the statement. Every countable subset of a well-ordered set has at least upper bound. So, let's consider the example of Mr. Justin, wherein A has an element of 1, 2, 3, 4, 5, and B has an element of all, or B is a set of all natural numbers. 1, 2, 3, and so on. is subset of B. So using the basic idea of transfinite induction, the first step, which is the base case. Here we consider the smallest countable subset of the well-ordered set. Since it is countable, we can list its element in the sequence. The first element of the set will serve as the least upper bound. Since Mr. Jackson provided us the countable subset, which is this set A. So it is said that the first element of a set will serve as the least upper bound. So the first element in set A is 1. So 1 is our least upper bound. Now, the second step or the last step is the inductive step. Here, we assume that any countable subset of well-ordered set with n elements that exists a less upper bound. So in inductive step that all preceding elements also holds the next element in the well-ordered set. Now let's consider the element we're in. Let's consider the countable subset with n plus 1, wherein we're going to add one more element. Now if we're going to add one more element in the countable subset, the first element, which is 1, let's call it B. So if you're going to add one more element that is less than or equal to B, our B remains our least upper bound. But if you are going to add one more element which is greater than our B, then the new element will be our least upper bound. Like for example, in this given set, our least upper bound is 1. If I were going to add 6, so 6 now is our least upper bound, since 6 is greater than 1. So in either case, adding one more element on countable subset, it has a least upper bound. So by using transfinite induction, we will be able to prove that every countable subset of a well-ordered set has a least upper bound. Since we are done discussing about transfinite induction, do you have any clarification regarding the topic? Since no one is asking, let's have another activity. It is a group activity. Same group like what you had earlier. I will give you 10 minutes to finish the activity. After the allotted time, we are going to check your answers. So, are you ready? Let's begin. Okay, class, give yourself a round of applause for finishing the activity. So again, what is transfinite induction? Yes, Miss Daniela. Yes, very good. So, how can we use transfinite induction to prove a statement about well-ordered set? Yes, Kim. Yes, that's right. How about Mr. Genesis? How can you use or apply transfinite induction in proving or solving problems involving infinite sets? Very good. Since you already grasped the content of our topic about transfinite induction, let's have our evaluation. Okay class, since we are done to our evaluation, let's have your assignment. Copy it in your math activity notebook. So this is our topic, transfinite induction. I hope you learn a lot of things from me. Thank you.